last class, I had worked out certain exercises essentially pertaining to Hermitian operators, their eigenvalues, their eigenvectors, and also established that if there are two commuting Hermitian operators, or equivalently two commuting Hermitian matrices, you are guaranteed that there is a complete set of common eigenstates of these two matrices. This can be extended to more than two matrices as well. Today I will continue to work out further exercises. And today's exercises would largely be related to operators and their algebras. You are already aware of the angular momentum algebra, where you had the spin generators satisfying the commutation relation commutator Sx with Sy is IH cross Sz, and that is a cyclic relation, because you could have a Z here and an X there and a Y there and so on. You could have written the commutator this way and therefore the algebra in this fashion, or you can define S plus and S minus as Sx plus or minus Isy depending upon the context, and S plus dagger is S minus. In that case, the equivalent way of writing this algebra is S plus S minus is 2H cross Sz, and Sz with S plus or minus is plus or minus H cross S plus minus. So this is by way of recapitulation. We certainly use this algebra extensively in the study of the spin doublet, the 2-level atom problem, and also the 3-level atom problem. Further, at one stage I derived the following relation: e to the minus I theta by H cross Sz Sx e to the I theta by H cross Sz is Sx cos theta plus Sy sin theta. Now this is something that tells us that Sx transforms like the x component of a vector. Similarly, if you had Sy here, you will have minus Sx sin theta plus Sy cos theta out there to tell you that Sy transforms like the y component of a vector, and so on. I did this explicitly in one of my earlier lectures by expanding out the exponential and then multiplying Sx across that and showing that indeed you get this as the answer, so that Sx transforms like the x coordinate, where x prime goes to x cos theta plus y sin theta under rotation by an angle theta, like that. On the other hand, later on I did put down an identity of this form: e to the lambda a b e to the minus lambda a is b plus lambda commutator a b plus lambda squared by 2 factorial commutator of a with b plus so on. We use that in the context of the displacement operator and the squeezing operator as well. At that time this identity was not proved, and I want to prove this identity now as an exercise. So I define f of lambda as e to the lambda a b e to the minus lambda a. Lambda is a parameter. It is clear that f of 0 is simply b. It is assumed that a and b are Hermitian matrices. That is what is of relevance to us. So f prime of lambda, that means the differentiation with respect to lambda, gives me a e to the lambda a b e to the minus lambda a minus e to the lambda a b, I bring down the a there, e to the minus lambda a, but I bring down the a there. And therefore, this object is a f of lambda minus f of lambda a. It is a commutator of a with f of lambda. It is clear that f prime of 0 is simply the commutator of a with b, because f of 0 is b. Similarly, I can find out f double prime of lambda. So, f double prime of lambda, clearly from here, if f prime of lambda is the commutator of a with f of lambda, f double prime of lambda is the commutator of a with f prime of lambda, and that is the same as, so f double prime of 0 is a with b, and so on. So, I can do the higher derivatives of f, and this is what I get for every term. Now, f of lambda is of this structure. It is a smooth function of lambda and therefore can be expanded as a Taylor series in lambda. So, I can write f of lambda as f of 0 plus f prime of 0 times lambda plus f double prime of 0 lambda squared by 2 factorial, and so on. Now, if I substitute, I get f of lambda, which is e to the lambda a b e to the minus lambda, is equal to f of 0, which is b, plus f prime of 0 times lambda, which is lambda a b, plus lambda squared by 2 factorial f double prime of 0 plus so on, and that proves the point. So, this is the identity, this is the general identity, e to the lambda a b e to the minus lambda a is b plus lambda times this commutator plus lambda squared by 2 factorial a with b commutator, and so on. So, clearly this infinite series will terminate if one of these commutators is 0. I use this specifically in the context of squeezing and displacement operators when we discuss the harmonic oscillator problem and quantum optics. Now, I would like to use this identity to establish this relationship. So, let me start with e to the minus I theta h by h cross s z s x e to the I theta by h cross s z. So, here lambda is minus I theta by h cross, a is s z and b is s x. So, this is what I have. If I now substitute, I have e to the minus I theta by h cross s z s x e to the I theta by h cross s z is equal to b, and b is s x, plus lambda times commutator of a with b, which is minus I theta by h cross, the commutator of s z with s x, plus lambda squared by 2 factorial the commutator of a with the commutator of a with b, that is s z with s z s x commutator plus so on. Now, I can work out these commutators simply because I know the algebra of the spin matrices, and then I have the following. E to the minus I theta by h cross Sz Sx e to the I theta by h cross Sz is equal to Sx. Sz with Sx is IH cross Sy, so that gives me plus theta by h cross Sy. So that is what I get from this term. Then I have the next term, which gives me a minus theta squared by h cross squared 2 factorial. The commutator of Sz with the commutator of Sz with Sx, which is IH cross Sy, plus so on, and this object is Sx plus theta Sy minus theta squared by 2 factorial IH cross by h cross squared. That is an Sz with Sy, and that is a minus IH cross Sx plus so on, and that is Sx plus theta Sy minus theta squared by 2 factorial Sx plus so on. Now if I work out the other terms, it will be clear that this will be Sx times 1 minus theta squared by 2 factorial plus theta to the power of 4 by 4 factorial and so on, which is Sx cos theta, plus Sy, the leading term is theta, then I have a theta cube by 3 factorial, theta to the 5 by 5 factorial and so on. And therefore, I get Sx cos theta plus Sy sin theta. So this is a simple way of establishing what I set out to prove by a brute force method earlier on. I got this relation by expanding out the exponential and doing the entire algebra. This is a neat way of doing this, provided I establish this identity. Now having said that, I wish to ask some more questions on the angular momentum algebra. We know that the orbital angular momentum components Lx, Ly and Lz also satisfy this relation, and therefore in general consider 3 Hermitian matrices Jx, Jy, Jz satisfying the Lie algebra. Jx, Jy commutator is IH cross Jz cyclic relation. Define J plus J minus as Jx plus minus Ijy, and then surely Jz J plus minus is plus or minus H cross J plus minus, and J plus with J minus is 2H cross Jz. Now J could represent the spin matrices, Jx could be Sx, Jy could be Sy and Jz could be Sz, or if we are discussing orbital angular momentum, Jx would be denoted by Lx, Jy by Ly, Jz by Lz, where L itself is R cross P. The algebra is the same, the situation is different. In the one case we are dealing with an intrinsic property called spin. In another case we are dealing with something in physical space called orbital angular momentum. The question that I wish to ask is the following. I know therefore that J squared and Jz commute with each other. I have already established therefore that there is a complete set of common eigenstates of J squared and Jz. Let me denote the eigenstates by J comma M. In the case of spin, this would be given by the label S, and M would be the third component of spin, the eigenvalue of Sz. In the case of orbital angular momentum, this would be replaced by L, and that would continue to be M, where now M denotes the eigenvalue of Lz. So j squared Jm, I know that there is an eigen state j comma m of j squared, and since j squared is a positive definite operator, recall that j squared is jx squared plus jy squared plus jz squared. I can well write this eigenvalue as lambda h cross squared. Lambda is to be determined, and it is clear that lambda is greater than 0. Now jz jm I know is m h cross ket j comma m. M too has to be determined given lambda. One thing is clear, that since j squared is jz squared plus some positive quantities, lambda is greater than or equal to m squared, and m squared itself by its very nature is greater than 0, greater than or equal to 0. So this is evident. We now need to find out the values, the set of values that lambda can take and the set of values that m can take. You will recall that when we did the 2-level atom problem, we had 2 eigenstates of spin. I labeled them ket s comma m and ket s comma minus m in the following sense. In the case of the spin doublet, we had half comma half and half comma minus half. So there was an s comma m, the same s with a minus m. This is what we had as the eigenbasis, the spin eigenbasis in the case of the spin doublet. And we simply noted the fact that m took values minus s to plus s in steps of 1. Similarly, when we did the 3-level atom problem and we had the same algebra as the angular momentum algebra or the spin algebra, we had 3 basis states and the values were 1 comma 1, 1 comma 0 and 1 comma minus 1. So when s was 1, again we realized that m took values minus s to plus s in steps of 1. We would like to see if in general this can be established. In other words, we want to find the value, the set of values that lambda can take and the set of values that m can take. It's clear that lambda is simply a function of j. M has to be determined in terms of lambda. We proceed to do this as follows. Let's start with the fact that j squared commutes with jx and j squared commutes with jy. Therefore, j squared commutes with j plus and j squared commutes with j minus. Recall that j plus is jx plus ijy and j minus is jx minus ijy. I therefore have j squared j plus this operator acting on the state j comma m to be equal to j plus j squared acting on the state j comma m. I know that this object is j plus times the number lambda h cross squared j comma m, and since that's a number I can pull that out and I have j plus jm. Call the state j plus jm as some ket chi. It's now clear that j squared chi is lambda h cross squared chi. In other words, we are saying that j plus acting on the state j comma m takes it to another state which I have represented by ket chi symbolically. That state is also an eigenstate of j squared with the same eigenvalue lambda h cross squared. Recall that j squared acting on the state jm gave me eigenvalue lambda h cross squared. Now it seems that j plus jm, this state, is also an eigenstate of j squared with the same eigenvalue lambda h cross squared. Therefore, when j plus acts on the state j comma m, the ket j comma m, it does not change the eigenvalue corresponding to j squared. On the other hand, consider the commutator jz with j plus. Now, jz with j plus is plus h cross j plus. Look at the state jz j plus j comma m. From this algebra, I have that jz j plus j comma m minus j plus jz j comma m is h cross j plus j comma m. Well, certainly this object jz acting on j comma m is mh cross, which is a number, and therefore I can pull that out and write the second term in this manner. Therefore, I have jz j plus j comma m, jz operating on this state which I labeled as ket chi symbolically. This is equal to m plus 1 h cross j plus j comma m. This was ket chi. I have therefore established that j plus acting on the state j comma m, the resultant state here, is an eigenstate of jz, but with an eigenvalue not m h cross, but m plus 1 h cross. Recall that jz acting on jm was m h cross jm. It is therefore clear that the operation of j plus on the state j comma m is as follows. It does not seem to change the j value, but it does change m to m plus 1. Now, let us look at what j minus does to the state j comma m. I repeat this argument. I start off with the fact that j squared j minus is equal to 0, and therefore j squared j minus j comma m is equal to j minus j squared j comma m. But this is simply lambda h cross squared j minus j comma m. Hence, I see that the state j minus j comma m ket is an eigenstate of j squared with eigenvalue lambda h cross squared. In other words, I have shown that j minus acts on the state j comma m without changing the eigenvalue. That seems to be the same. And since lambda is a function of j, it looks like j is not changing when j minus acts on j comma m. So, whatever I said about j plus acting on j comma m also holds for j minus acting on j comma m, in the sense that the j value does not change. On the other hand, I know that the commutator jz with j minus is minus h cross j minus. Therefore, if I acted this commutator on the state j comma m, I get the following. I know that this is m h cross j comma m. It is therefore clear that when j minus acts on the state j comma m, it reduces the m value by 1, takes it to the state j comma m minus 1, when j minus acts on j comma m, and when j plus acts on j comma m, it takes it to a state where the m value increases by 1. It's in this sense that we say that j plus and j minus are the lowering and the raising operators respectively. They leave j untouched, but change the third component value m. J minus decreases it by 1 and j plus increases it by 1 if it acts once. It is clear that if j minus acts twice on j comma m, this means it acts twice on j comma m, it takes it to the state j comma m minus 2, and if j plus acts twice, it takes it to the state j comma m plus 2. In this sense, they are raising and lowering operators or ladder operators. However, this cannot go on indefinitely, because if j plus acts p times say on j comma m, from whatever I have shown you till now, this takes it to a state j comma m plus p. But I have a constraint. I have the constraint that lambda corresponding to the eigenvalue of j squared is greater than or equal to m squared, and that of course is greater than or equal to 0. We began there. So you see, this cannot be increasing indefinitely, because there should come a stage where if I denote m plus p by m prime, there should come a stage corresponding to some p where m prime squared cannot be greater than lambda. So there must be an upper value beyond which j plus cannot increase the third component value by 1. In other words, I have the following condition now. I realize the following, that there is an upper bound of m, which I will call m plus, such that when j plus acts on the state j comma m plus, it gives me 0, because otherwise m plus squared could be greater than lambda, and lambda is a function of j. Similarly, I know that there must be a lower bound for the same reasons. There is an m minus. Every time j minus acts on m, it reduces the value of m by 1, but then there must be an m minus, which fixes the lower bound, because j minus acting on j comma m minus must be equal to 0. Simply because this constraint has to be satisfied. Look at the first relation. I therefore have j m plus, j plus dagger, which is j minus, is equal to 0. Consider the object j m plus, j minus, j plus, j m plus. It is clear that this is 0, because j plus acting on j m plus is 0. Similarly, the j minus acting on this side on j m plus is 0. But I can write j minus j plus in terms of j squared and jz in the following manner. J minus j plus, when written in terms of jx and jy, is jx minus ijy times jx plus ijy, and this object is jx squared plus jy squared plus I, commutator of jx with jy, which is ih cross jz. But that is the same as j squared minus jz squared minus h cross jz. I therefore feed that in there, and I have j minus j plus sandwiched between these states is the same as j m plus j squared j m plus minus j m plus j z j m plus minus h cross j m plus, that is a j z squared, this is a j z j m plus. I have this, and this object I know is 0. But these j m plus is an eigenstate of j squared, j z squared and j z. So, I might as well pull out the eigenvalues. And then I have the following. I have 0 is equal to, the first term gives me a lambda h cross squared. These are normalized states. So, the inner product of j comma m plus bra with j comma m plus ket is 1, and therefore, I just get lambda h cross squared from the first term minus m squared h cross squared from the second term minus m h cross squared from the third term, which tells me that lambda is equal to m into m plus 1, except that in all these cases it is m plus. It is m plus times m plus plus 1. So, this is the first relation I get, which relates lambda to the upper bound on m, which I have denoted by m plus. I can repeat this calculation starting with the fact that j minus acting on the state j comma m minus is 0. Therefore, I have this object to be 0. But once more I can write this in terms of j squared, j z squared and j z, because j plus j minus product is jx plus ijy times jx minus ijy, that is jx squared plus jy squared plus I commutator of jy with jx. The commutator of jy with jx is minus I h cross jz. This therefore tells me the following. I have j plus j minus equals j squared minus jz squared, because I have written jx squared plus jy squared in that fashion, plus h cross jz. Taking the expectation value in this manner, this object is 0, remember, is simply the following. As before, I have this minus this object plus h cross that gives me a j squared, a lambda h cross squared. It pulls out a lambda h cross squared. This pulls out plus m squared h cross squared, except that m is now m minus, comes with a negative sign because of the negative sign here, plus m minus h cross squared. Since this object is equal to 0, I have lambda is equal to m minus times m minus minus 1, and that is the second relation that I have. So, I have two descriptions of lambda. Lambda is m plus times m plus plus 1. It is also equal to m minus times m minus minus 1. I emphasize that m plus is the higher bound on the value that m can take for a given j, and m minus is the lowest value that m can take for the same value of j. Since these two are equal, I have the following. I have m plus times m plus plus 1 is equal to m minus times m minus minus 1. Well, this tells me the following. I can have one of two solutions. I can have m plus is m minus minus 1. Certainly that is satisfied, or m plus is equal to minus m minus. This is another possibility. We need to understand that this is not possible. This is not possible because if I had started with the state j comma m minus and repeatedly applied j plus on it to the power of p perhaps, I would have landed in a state m minus plus p, and m plus was the highest value that it could have taken, as a result of which m plus is greater than m minus. The difference between m plus and m minus has to be an integer, because every time j plus acts on the state, it increases the m value by 1. And therefore, I know that the difference m plus minus m minus is an integer. I also know that m plus is the upper bound and m minus is the lower bound on m, and therefore this relation is not true, whereas this is more acceptable. And therefore, if m plus is equal to minus m minus, m plus minus m minus is 2m plus. The solution is this. Since lambda is simply a function of j, I now have m plus minus m minus is 2m plus, and m plus is j, and therefore m minus is minus j. And therefore m plus minus m minus is 2j. But this is an integer. Therefore, j takes values 0, half, 1, 3 by 2, and so on. If this is 0, of course it is 0. If this is 1, it is half. If it is 2, it is 1, and so on. And m can take values minus j to plus j in steps of 1. And lambda itself is therefore j into j plus 1. It is j into j plus 1. So what we have established is the following. Simply on the basis of the SU2 algebra, we have established that j squared acting on jm is j into j plus 1 h cross squared j comma m. Jz acting on jm is m h cross j comma m. J takes values 0, half, 1, 3 by 2, and so on. It takes integer or half integer values. For a given value of j, m takes values minus j to plus j in steps of 1. You will recall that this was m plus and that was m minus, the upper and lower bounds on m. And every time j minus acted on a state, it reduced the value of m by 1. If j plus acted on the state, it increased the value by 1. And therefore, m takes 2j plus 1 values over the range minus j to plus j for a given j. Ranging from minus j to plus j in steps of 1. And indeed, this is what we had verified when we did the spin doublet problem, equivalently the two-level atom problem. When we had the two basis states half comma half, where J was half, called it S then because it was spin. The second entry was M. So we had two states half comma half and half comma minus half. So M took values minus half to plus half in steps of 1. When we did the three-level atom problem, we had the states 1 comma 1, 1 comma 0 and 1 comma minus 1. Once more, for a given value of J, in this case it was 1, M took values minus 1, 0 and plus 1, ranging from minus J to plus J in steps of 1. We can now proceed and find out what exactly is the action of J plus on J comma M. We have realized that J plus is a raising operator. It takes J comma M to J comma M plus 1. But what are the coefficients? What is the coefficient outside? So for doing that, we need to find out this object. We need to find out this object. What is it that multiplies this get J comma M plus 1? This can be handled in the following fashion. This is what I have when I take the Hermitian conjugate. So I consider the object Jm, J minus J plus Jm. It's pretty clear that J plus will increase the M value to M plus 1, and therefore this would go to a state J comma M plus 1. But J minus will act on that state and decrease the M value by 1 again, bringing it back to J comma M, and then the orthogonality relation, the fact that J comma M inner product with J comma M is 1, that will give us a number. That's precisely what is happening. And as we did earlier, we can substitute for J minus J plus. So J minus J plus was J squared minus Jz squared minus H cross Jz. This is what I have. It's also clear that this object can be written as J plus Jm squared, mod squared, because J plus Jm is like some ket chi. This is like the bra, and therefore this is like mod square of that object. The coefficients are in general, the coefficients here are in general taken to be real, and therefore if I evaluate the number here, that will be the square of the coefficient that I will need here. So this object is J into J plus 1 H cross squared minus M squared H cross squared minus M H cross squared. This is the same as H cross squared J into J plus 1 minus M squared minus M. This is the square of the number that comes here, and therefore the number that comes here can be easily evaluated. I would like to write J into J plus 1 minus M squared minus M as J minus M into J plus M plus 1. That's a way of writing it. And therefore, J plus acting on Jm is the square root of J minus M into J plus M plus 1. There is an H cross J M plus 1. The H cross was because I needed to take the square root of this object, and therefore I got the H cross. The H cross is outside the square root. It's clear therefore that when J plus acts on the state J comma J, which is the maximum value that M can take, that gives me 0. which is consistent with what I wanted. The j comma j was the uppermost state that I can have, and j plus cannot raise the m value beyond that. Similarly, I can find out the effect of j minus acting on j comma m. Quite apart from taking this state to the state j comma m minus 1, what is it that multiplies it? What is the constant that multiplies it? Some number. So I need to find this number. As before, I try to find this. That's going to be j comma m. J plus j minus is j squared minus jz squared plus h cross jz, j comma m. As before, I have this to be j into j plus 1 minus m squared plus m h cross squared. And this can be written as root of j plus m into j minus m plus 1. It is simply a way of writing it, the whole squared. From which it is clear that j minus acting on the state j comma m gives me root of j plus m into j minus m plus 1 h cross j comma m minus 1. Once more, it is clear that when j minus acts on the state j comma minus j, that is the lowest value that m can take. I referred to this as m subscript minus earlier on when I did the derivation. This object is automatically 0 because j minus j is 0. That is what I want. There is a lower bound, and j minus acting on that state gives me 0. To summarize, therefore, I have gotten for you the angular momentum algebra and the manner in which these states act, the operators act on the states. I have j squared acting on j m is j into j plus 1 h cross squared j m. J z acting on the state j m is m h cross j m. M taking two j plus 1 values ranging from minus j to plus j in steps of 1. I have j plus j m is root of j minus m into j plus m plus 1 h cross j m plus 1, and j minus acting on j m gives me this. So this is the manner in which the angular momentum operators act on the basis states j comma m. What I said holds for spin matrices, where j is replaced simply by the label s, and orbital angular momentum, where jx, jy, jz are denoted in this context as Lx, Ly, and Lz, being the x, y, and z components of the orbital angular momentum operator.